Welcome back. For today's video, let's do some linear least squares approximation. So suppose I had this data. At time 2.9, I measured some measurement, I got 4. Time 4.4, I measured 4.4 again. At time 4.9, I measured 5. And 6.9, I measured 6.1. And I wish this data lay on a line. Maybe it doesn't, but let's pretend that it did, a line like c plus dx. And if this data did lie on a line, and the time is the sort of x-coordinate and the measurement is the y-coordinate, then you get 4 equations. I would say plug in 2.9 and you should get 4, plug in 4.4, you should get 4.4, plug in 4.9, you should get 5, and plug in 6.9 and you should get 6.1. But that's a system of equations with not enough unknowns. There's too many equations. There's no solution to this. It's inconsistent. And that's, in essence, the whole point in least squares. When I have an inconsistent system, like in this case, if I write the matrix of this equation, it goes like this. That's what I've got written here, times CD equals the, let's call this the data vector for 4.4, 5, 6.1. That's often called the data vector, and maybe I'll name it even y. And maybe I should name this matrix A. So this solution A times CD equals y doesn't have, this equation, this matrix equation, doesn't have a solution. And that's, in essence, because this data vector y doesn't lie in the column space of A. So you can ask yourself, well, if y doesn't live in the column space of A, maybe there's something that is in the column space of A that's very close to y. How close? What is the closest possible thing that we could pick? So what member of the column space of A is closest in Euclidean distance to y? And maybe I don't want to know exactly what that member is, but rather I want to know what C and D send A there. Does A send to that closest point? Because that'll be my slope for my best fit line. Slope and intercept. So again, I have this A and this Y, and again, all I do is when I don't have a solution to AX equals Y, I essentially multiply on both sides by A transpose. As long as A had linearly independent columns, this will have a unique solution, and it will be the least squares solution. So A transpose A, in this case, if you multiply it out, looks like 4, 19.1, 19.1, 99.39. Which we'll talk about the condition number of matrix sometime soon. This one's not especially well conditioned. And so what you're trying to do then is to solve A transpose A times CD equals A transpose Y. If you multiply that out, you find it's 19.5, 97.55. And this has a unique solution. I have a 2x2 invertible matrix because the Gram matrix A transpose A is guaranteed to be invertible since the columns of A were linearly independent. And so the CD that I get out is 2.87 and 0.542. So C here is the y-intercept and 0.542, that's D, that's the slope. So if you plot those 4 data points in your favorite free graphing calculator on the internet, then you'll see that it looks like this. And if you plot the line that I just pointed out, there it is. And that is the best fit line. The distance, the vertical distance from those data points to the line, the sum of squares of those vertical distances is the smallest possible when I choose that line. That's what I mean by the least squares. So, well, the closest point in the column space, which was the original question I asked, it looks like A times that, 2.87, or 2.28, 0.54. A times that. I don't really care very much what the actual, since my data vector wasn't in the column space of A, I'm not really interested in the closest point. I'm more interested in the vector that A takes to that closest point. That's the least squares solution. So there's no reason that I have to stick with lines. I could do this with cubics or quadratics or fifth-degree polynomials if I feel like it. So let's suppose I wanted a cubic and the coefficients were C, D, E, and F. And I want them to fit this data, and that data is stolen directly from cosine of x on 0 to pi. If you plug in the t values into some arbitrary polynomial, c plus dx plus x squared plus fx cubed, then I'm writing down here the equations that you would get. Just plug in 0, and you're supposed to get 1. Plug in pi over 4, and you're supposed to get root 2 over 2. And eventually, okay, plug in pi, and you're supposed to get minus 1. Again, this system of how many equations? 1, 2, 3, 4, 5 data points. So I have 5 equations, and I have only 4 unknowns. It turns out that there's absolutely no way you can have a solution to that. So we can ask, what's the least squares solution? Well, how do I go about finding that? I take A to be the coefficient matrix. So that's going to look like all 1s, and then the data 0, or so the inputs 0, pi over, okay, 0, and then 0 squared, and then 0 cubed, and then pi over 4 squared, pi over 4 cubed, pi over 2, pi over 2 squared, pi over 2 cubed, etc. So this kind of matrix is called a Vandermonde matrix, Vandermonde, Vandermonde, and it is always invertible. As long as you choose your t's at different points and you choose the size correctly. Clearly we don't have a correctly sized Vandermonde matrix because it's not square, it can't be invertible. But in any case, you want to solve A transpose A equals A transpose, oh, that should say A transpose A X equals A transpose Y. So that is a typo. Right there, we will try to fix that in post-production. A transpose A X equals A transpose Y. So when you do that, you compute A transpose A. The numbers are kind of messy, so I decided to skip the details here, but the solution that you get for the X is this, 0.9989, 0.01923, minus 0.631, and 0.1346. What's the interpretation of that? C is the constant term. Let's see if I can get this on the screen a little bit better. Yeah, there we go. Okay, so here is my cubic polynomial. The red points are the data that I've plotted. And lo and behold, I've got a cubic that looks like it's a really good match for cosine, just on the interval from 0 to pi. Okay, let's keep going. Suppose I have this e to the cosine t, and I want to sample it on 0 to 2 pi at the reasonable normal points that you do, and I wanted to approximate it like a c plus a d cosine t plus an e sine t. Your matrix A comes in the same way. You just plug in those values for t into one cosine and sine, and you get the following matrix A. Just plug them in. Now, if you multiply out A transpose A, you get the following matrix, 510, 130, 002. You know that's always got to be symmetric. And if the columns of A were linearly independent, then you know it is invertible. So the solution, there is a unique solution to A transpose AX equals A transpose Y. A transpose Y I've written out for you here. You should check that that's what you get. The C, D, and E that uniquely solve A transpose A, C, D, E equals A transpose Y, that's the least squares approximation. That's the C, D, and E that are the best coefficients, are these, 1.3, 1.25, 0. So the best thing to do is leave off sine of t altogether if you're trying to approximate e to the cosine t. Your best polynomial is 1.31 plus 1.253 cosine of x if you want to look for these 5 points and e to the cosine t. Maybe I can get a graph of that to come up. Let's see. Again, we'll try to fit that nicely onto the screen. So here's my e to the cosine t, e to the cosine x. And it's a periodic function, but it's wonky. It's not really quite a trig function. And let me plot the... that blue line is the cosine that I plotted out for this. I don't think that I had plotted the 5 points that I got it from. You see, it's not exactly great, and that's because I'm only checking it at 5 points. I'm guaranteeing that it's close to 5 points on that curve, not super close to the curve everywhere. If I chose my 5 points wisely, then maybe I would get a good approximation of the function everywhere. Okay, so here, but nevertheless, if you use this easy curve and integrate it, you'll get an approximation of the integral of e to the cosine t. If you integrate that, well, if you integrate that, you get 8.23, which is really not a bad approximation for 5 minutes work. The first integral that we did, e to the cosine t, I can't integrate that. Wolfram Alpha can integrate that for me, but I can integrate this function using my brain and a calculator, even no calculator if I need to. But let's try another approach. Let's try to minimize the distance in the function space, in a function space, using the inner product on functions. You know that gives you a length on functions. So suppose we did a polynomial approximation that looks like some powers of t. The Gram matrix for that, and that's going to be my k, looks like I should take the basis, that's 1, t, t squared, and so on, and compute all the inner products between the t to the i's and the t to the j's. So, for example, if I was just doing a quadratic, then the Gram matrix would be this 3x3 matrix here, and you know it's symmetric because this inner product is an inner product, it's symmetric. Which means in order to compute the Gram matrix at all, I need to know how to do a bunch of integrals. The integral of 1 times 1, the integral of 1 times t, the integral of 1 times t squared, and so on. The integral of, t times 1, the integral of t times t, the integral of t times t squared, the integral of t squared times 1. You know this is symmetric, so I really only have to do half of it. And the integral of t squared times t squared. So you compute all those integrals, and you find, for the quadratic, you get reasonable numbers on 0 to 1. So you get this. This is called the Hilbert matrix, or maybe its inverse is called the Hilbert matrix. You can read about that in your book. He goes on about it for a while. It's a famous example of an ill-conditioned matrix. And we'll talk about condition numbers soon. So I'm trying to let's try to approximate e to the t by a quadratic on the interval from 0 to 1. If I do that, then I should take this vector f. That's 1 with e to the t, the inner products of 1 with e to the t with e to the t, and t squared with e to the t. Compute those integrals, and you get the following numbers. If I set f to be that, then finding the closest p is exactly the same as minimizing the quadratic polynomial, this polynomial that you have seen lots of times before. Only that shouldn't be norm f squared, that should be norm of e to the t squared. Let's talk for a sec about why that is. Well, where does that minimum occur? Exactly when kx equals f, which means, again, you're just doing Gaussian elimination. You're just trying to row reduce. Let's see if we can write it out. So if you row reduce that system of equations, you'll find that the coefficients of your quadratic are these, 1.01, 8.85, and 0.84. And that gives you a quadratic polynomial that looks like 1.0129 plus 0.8515 t plus 0.8388 t squared, which approximates the function e to the t across the whole interval from 0 to 1 without having to bother with Taylor series. Taylor series get better and better as you add more terms, and this technique doesn't do that. But I also don't have to take any derivatives ever. So again, I'm not sampling the points of e to the t anywhere. I'm working in a function space. Now the point is that, let's call this p tilde of t, that's my least squares approximation. The error in this function space, which is called L2, is just the square root of the integral from 0 to 1 of the square of the difference between those two functions. That's just the norm of the difference. That's how far away they are from each other in this vector space with this notion of length. And they're pretty close, 0.05. You can read about this in your book for more details. Let's approximate one more thing before we wrap up. e to the cosine t plus sine t on 0 to 2 pi with the same norm, but now I'm going to integrate from 0 to 2 pi. And let's suppose I looked like I wanted a cosine, a sine, and a cosine squared. My Gram matrix becomes nice. So again, I take the basis 1 cosine t, sine t, and cosine squared t. It's a basis of something, of a 1, 2, 3, 4-dimensional space. And take the inner products of all of the members with themselves in an organized way. That's all the Gram matrix is. I'm just taking inner products of members of a basis in some inner product space. It's, in this case, function space. So on the first row, I'll take the dot product of 1 with every member of the basis, and then in the second row, the dot product of cosine with every member of the basis, and then sine in the third row with every member of the basis. And finally, in the fourth row, I'll have a dot product of cosine squared with everything in the basis. Doing those integrals is perhaps tedious, so I'd rather avoid showing you all of the details, especially given that most of them are from your calculus class. Maybe all of them are directly from your calculus class. So we'll skip that. Write down, this is the Gram matrix, and so in essence, all you have to do is take k to be this, and I'll just tell you what all of those integrals are. It's 2 pi, down the diagonal are the nice ones, 2 pi, 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 and 3 pi over 4. You wish it was zeros, but cosine squared is not orthogonal to the rest of these polynomials. So the point is that cosine squared is not orthogonal to 1. So you get pi, that's fine. Take f to be the vector 1 with the function you're trying to approximate, and then the dot product of 1 and the function you're trying to approximate, the dot product of cosine and the function you're trying to approximate, the dot product of sine and the function you're trying to approximate, and the dot product of cosine squared and the function you're trying to approximate. Again, this is going to be a bunch of integrals. Maybe you can't do these integrals, but Wolfram Alpha can do them for you at least. When you do them, you get the following numbers out: 7.95, 3.5, pi, and 4.4. So you're going to solve kx equals f. These are going to give you the coefficients c plus d cosine plus e sine plus f cosine squared. Multiply, or don't multiply, take the inverse if you like. Solve that system of equations to get c, d, e, and f have to be, there's a unique solution, this, 0.995, 1.13, 1, and 0.543. What does that mean? That means I think that 0.995 plus 1.13 cosine of t plus sine of t plus 0.543 cosine squared of t is a good approximation on the interval from 0 to 2 pi of my original weird crazy function e to the cosine t plus sine t. You'll notice this coefficient on sine t is really nice here. It's 1. That's because I artificially added a sine t to my e to the cosine t when I constructed this example. Well, let's graph them. So e to the cosine t plus sine t looks like this on the interval from 0 to 2 pi. Of course, it's periodic. And if you plot this nice quadratic in trig functions, you get that, which is very similar, very close. So again, let's name that approximate p of t. And so to compute how close you got, you should take the norm of p of t minus the function you're trying to approximate. And again, to take the norm, you take the square root of an integral from 0 to 2 pi of, well, that thing squared. So it's 0.995 plus 1.13 cosine t plus sine t plus 0.543 cosine 43 cosine squared t minus e to the cosine t minus sine t. You see those sine t's cancel out. That was on purpose. Oh, no, this whole thing has to be squared. The integral of the function squared. Take the square root of that. At the end of the day, you find that it's 0.079, which tells you that in this function space, the distance between your approximating polynomial and this function is 0.08. It's called an L2 approximant, or approximation. It's a pretty good approximation, and you can do things with it that are hard to do with e to the cosine t plus sine t.